Before we go to convection, I'd like to give two more assignments on the problem that we have just now solved, that is for 1D transient heat conduction. One problem that I'd like to give is
So, would you please start the recording from your end?
okay. Suppose we have a plain wall that has some internal heat generation, and initially it is at a temperature Ti, and suddenly the two walls, their their let me their surfaces are brought down to a temperature of Ts. Initially you have a plain wall that has a temperature of Ti, and suddenly at time t greater than 0, the two walls are made to Ts, similar to the earlier problem. Only thing, there is a heat generation in that wall. So how to solve the problem for u as a function of x and time, the temperature as a function of x and time. I just give you some hint, and then you how to solve, and then you solve this problem. And then an identical problem I'd like to give. This is another problem, that we have a plane wall without any internal heat generation, and the plane wall is at an initial temperature Ti. In a dimensionless form it may be equal to 1, and suddenly one wall, that is the right hand side wall at x equal to L, that wall is cooled down to a temperature Ts, and the other wall, that is at x equal to 0, that is still maintained at the initial temperature of Ti. The whole block was at a temperature Ti, and suddenly the right hand side wall is cooled down to a temperature of Ts, and the left hand side wall, it remains to its old temperature of Ti. Okay. Then how to solve this problem? We can eliminate these things, these two, and all these things are not necessary here. How to solve, just I'll touch upon and then we'll switch over to the convection heat transfer problem. The method is very simple. That method is known as, there are many other methods. I discuss only one very simple approach that is known as the method of partial solution. There is a method that is known as the method of partial solution. There are other methods like maybe Laplace transform, maybe variation of parameter method, integral transform method. Those are the different methods that are there, but I'll discuss only one method. Very simple thing is the method of partial solution. I'll just show how this method is used for solution of any one of such problem. Let us say this problem number, assignment number 2. There what we will do is that we'll assume that this problem in terms of u, which is a function of x and time, this we can take it as this u is small u, the solution for which we are seeking for, that is the temperature in a dimensionless form we have written over here. This we can write it as a consisting of two separate problems. One is only a function of x, and then there is another problem that is a function of both x and time. We can have two different problems. One problem is a problem in terms of v, which is only a function of x, and there is another problem that is in terms of w, which is again a function of x and time. And the problem for which we are seeking for the solution, that is u as a function of x and time, that we can write it as if it is addition of two problems consisting of v as a function of x and w as a function of x and time. Now we'll try to find out a solution for v separately, try to find out a solution for w separately, and then if we add the solution for v and w, then it basically gives us the solution for the problem in terms of u. And this is what is known as the method of superposition. This is known as the method of superposition. That, let me explain what is that and when this is applicable. This method of superposition is applicable when the problem we are solving, this is applicable when we are solving a linear problem. And we have explained what is a linear problem. That a problem where the unknown has a power of 1. Hello?
है बोलना sir.
There may be some problem where there is a product of u into u square, or u del 2 del x square, like that. No such thing is there in this problem. All terms containing u, they have a power of to the power 1. Here u contains a power of 1, here power of 1 in the boundary condition of also u to the power 1. So when these type of things are there, then we call it a linear problem. And for linear problems, we can add two problems to get a solution for our desired answer. Now we define this problem V as if like this. This problem V consists of where because V is only consisting of X. So we define a problem like this. And subject to boundary condition that V at 0 is equal to 0 and V at 1 is equal to 0. And there is no initial condition for V, because V is there. So V is a problem that represents a steady state problem, and in this V we take care of the heat generation term. And there is another problem that is in terms of W. In that we have and subject to boundary conditions like this, identical to this. So if we split up the problem into two sub-problems, one is আবার কোথায় গেল? So we divide our problem in terms of U into two sub-problems. One is in terms of V, that is a steady state problem, where V is a function of x only, not dependent on time, such that d2v dx square is plus q equal to 0 with two boundary condition. V at x equal to 0 is 0 and V at x equal to 1 is also equal to 0. And then we have another problem in terms of del 2u del x square is equal to del w del t, something similar to our original problem. আমি একটা ক্লাসে আছি, ক্লাসের পর আপনাকে ফোন করছি একটু পরে। So if we can solve this problem. What is the solution for this thing we have already done? We have worked out this type of problem where there is internal heat generation and the two walls are maintained at maybe at two different temperatures at the same temperature. We have also found out a solution for this type of problem just now we have done. So once we find out the problem for these two, then if we add the solution for V and W, we get the solution for U. This is what is known as the method of partial solution that you can do through the method of superposition, and this is applicable for what you call for linear problems. Okay, so with this we'd like to conclude our discussion on convective heat transfer. Now we'll switch over to convection heat transfer.
Sir, would it be possible to share this Word file with us?
Yes, I'll just after this class I'll transfer the whole thing.
Thank you, sir. Thank you, sir.
Now we go to discussion of the convective heat transfer problem. This is a typical problem that we are dealing with most of the time that we come across convection problem. What is a convection problem? That we have a wall and in contact with the wall there is a fluid, and if the wall temperature and the fluid temperature they are different, then there will be heat transfer from the wall surface to the fluid, and the mechanism of this heat transfer is by convection. And so far when we have dealt with convection from a wall, we require to know what is the value of the coefficient of convection heat transfer, and once we know that coefficient of convection heat transfer, which we frequently use as a symbol, symbolically we represent it by a symbol H. So if we know the value of H, then we can solve for the problem of conduction heat transfer in the wall. We have a wall, one surface of that wall is exposed to convection, and if there is a convection, if we know the value of H, then we can find out the convective heat flux will be equal to H into wall temperature minus fluid temperature, and accordingly we can find out the wall heat flux. Now the question is, how do we get the value of that convection heat transfer H? And that is the central point of most of the studies in the area of convection heat transfer. This subject of convection or heat transfer, it tries to find out the value of H, that is the convection heat transfer, in different problems where there is a convection from a solid wall to a fluid, or maybe from a fluid to a solid depending on the magnitude of their respective temperature. If the solid is hotter than the fluid, then there will be convective heat transfer from the solid wall to the fluid, and if the fluid temperature is higher than the wall temperature, then the heat will be moving from the fluid towards the wall. Now either way, this transport of heat is by the mechanism of convection. Whether the heat flows from the wall to the fluid or from the fluid to the wall, the mechanism of heat transfer is by convection, and in convection heat transfer, we require to know what is the value of that H. If it is given, we can solve for the conduction problem in the wall. But the question is how that value of H is obtained. That is a question that is being addressed in this subject of convection heat transfer. And there may be different possibilities. This is one such case that we have shown. What is that thing we have shown is that there is a solid wall, and this wall may be, in this wall there may be a constant temperature of the wall, or maybe that we do not know the temperature of the wall, but we know the heat flux from the wall. The wall may be a horizontal one, or it may be a vertical one, it may be an inclined wall, and the fluid that is in contact with this wall, that may be a moving fluid with a known velocity of travel and the temperature is known, or it may be a fluid that is otherwise not moving with a fixed velocity, but it is otherwise a non-moving fluid, a fluid which is not having any other motion due to some external prime mover like a fan or a blower, but the fluid moves when it comes in contact with the plate. It picks up the heat, and because of picking up of the heat, the fluid becomes lighter in density, it expands in volume, it becomes lighter, so it starts moving upward, and it experiences a force of buoyancy that acts against the gravitational field, and it moves upward. So there is a motion created, and that motion is known as the natural convection or natural circulation or buoyancy induced convection. So this convective motion of the fluid, that may be because of buoyancy driven flow, which is known as a natural convection, or the movement of the fluid may be caused by some external agency like a blower or a fan where the velocity is known. So possibilities are that there is a hot wall with a known temperature, or there may be a hot wall with a known value of heat flux, and this wall is in contact with a colder fluid medium, and the fluid medium may be moving because of forced convection, or it may be moving because of natural convection. Either way, there is a convection, and when there is a convection heat transfer, what is the value of H, the coefficient of convection? That we want to know. That is the only thing, not the only thing, that is one of the prime thing of interest for convection heat transfer. So here we are showing one such wall, and this wall, sometimes it is called as a flat plate. It may be in the form of a flat plate, it may be in the form of a curved plate like in the wall of a pipe. Here we have shown a flat plate is there, and that has a beginning, and it may be quite a long one, infinitely long one, and the fluid is otherwise moving with a velocity of u infinity, and as it comes in contact with the wall, the fluid slows down, because on the wall the fluid velocity becomes zero because of the viscosity, the no slip property of this fluid. It may stick to the wall, and so the velocity of the fluid will be zero, and as you move away from the wall, the velocity of the fluid will be increasing, and beyond certain distance the fluid will again assume the same velocity u infinity beyond this distance, and this distance is called the boundary layer thickness, and the zone inside is called the boundary layer zone, and the zone beyond this is called the free stream zone. So this velocity is called the free stream velocity. This within the boundary layer zone, the velocity increases gradually from the zero velocity of the plate to which it is sticking, and it increases gradually to the free stream velocity, and in the free stream zone the velocity is uniform, and that is equal to u infinity. Now this thickness of the boundary layer, it is not constant. What we will see is that this thickness of the boundary layer will increase with x in a particular manner, and so that the boundary layer zone is not a zone of uniform width or thickness, rather it is a zone whose thickness is increasing gradually from 0 at this point, which is called the leading edge of this flat plate. At the leading edge, the thickness of the boundary layer is 0, and then it grows gradually. And similar to this, just as the velocity will increase from the 0 velocity of the plate to the free stream velocity, the old free stream velocity of this fluid, similar to that, we will observe a similar phenomenon in terms of the thermal behavior of the fluid. That is, if the wall has a temperature of T0, then at the wall, because the fluid is sticking, so under steady state, the fluid temperature also will be equal to T0, the same temperature as the temperature of the wall. The wall and the fluid both will have the same temperature of T0 on the wall. And if you go far away from this wall, you will not sense any difference in temperature of the fluid. What you will observe is that the temperature of the fluid will be equal to the same free stream temperature T infinity. This temperature is the temperature of the free stream fluid that we indicated in terms of T infinity. So if we measure the temperature in the free stream, we will see that the temperature will be equal to T infinity. Uniformly it will be T infinity. But as you approach towards the hot wall, you can beyond certain distance from the free stream, you will see that you can progressively sense the temperature of the fluid. Here it will be maximum, that is equal to T naught, but as you move away, you see that temperature is somewhat less, and as you go upward, you see that the temperature is approaching towards the free stream temperature. So again, you can divide this zone of fluid into two parts. One part very close to the wall. In that part, the temperature will be a varying one from the wall temperature of T0 to the free stream temperature. And there is another part. In that part, the temperature is uniform, that is equal to T infinity. So there are two parts of the fluid stream. One part very close to the wall, where the temperature of the fluid will vary from the wall temperature up to the free stream temperature, and outside that zone there is a zone known as a free stream zone, where the temperature will remain uniform to the free stream temperature. Now this zone where the temperature is varying is called a thermal boundary layer zone, and the temperature in the zone where the temperature is not changing, that is called the thermal free stream zone. Here, so that we can have two such phenomenon, one in terms of velocity will be varying inside the boundary layer zone, that is called a hydrodynamic boundary layer zone, and outside there is a free stream zone. Similarly, just like we have a boundary layer zone in terms of velocity, that is called the hydrodynamic boundary layer zone. Similarly, there are two zones in terms of temperature variation. The zone inside is called the thermal boundary layer zone, and outside it is a free stream zone, thermal free stream zone. And these two zones, they are in fact they may be distinct in most of the cases. That is the velocity boundary layer zone and the temperature boundary layer zone. They will be two distinct zones, and the thickness of this thermal boundary layer zone, that is shown with a different symbol delta with a suffix t, just to make it distinct from the velocity boundary layer zone. This delta represents the thickness of the velocity boundary layer zone, and delta t represents the thermal boundary layer zone. And these two zones are distinct such that the value of delta and delta t, they will be distinct at the same value of x. This delta is a function of x, delta t is also a function of x, but their functional dependence with x will be may be different for delta and delta t. They may be different. Delta may be greater than delta t for some type of fluids. In some other fluid, we can see delta may be smaller than delta t. In some case, the velocity boundary layer zone may be thicker than the thermal boundary layer zone. In some other case, the velocity boundary layer zone may be thinner than the thermal boundary layer zone. And in some other case, the thickness of the two boundary layer zones also can be same. Now, coming back to the coordinate system, at the starting point of this flat plate, which is known as
Sir,
the,
can't it happen that we have delta equals to delta t,
it
certain
can
conditions?
it is also a possibility. There may be some other case of range of fluid where delta and delta t, they may be very close to each other. In some case, they may be distinctly different, and both possibilities are there. Delta may be much greater than delta t, delta may be much smaller than delta t, and in some case delta and delta t may be very close to each other.
And sir, in these cases, we are considering the internal heat generation to be zero.
That we can take, we may not take. I did not go into much complexity into this thing, just I am trying to introduce the complexity and how to address that, to how to find out the value of H. That is what I am trying to address for different situation. There may be a fluid where there may be a heat generation also. You are talking of heat generation inside the solid or fluid?
Solid wall.
Solid wall we are not bothered about. Now we have come to the fluid zone.
Okay.
The fluid zone is bounded by a solid wall. When we are solving for the solid wall, we did not bother about the fluid zone. Only thing that was a matter of concern for us, how to get the value of H. Once we know the value of H, we can solve for the solid zone problem. Now question is, how do we get the value of H? That is the question that is being tried to be answered in the subject of convection heat transfer. If somebody gives you the value of H, then you can find out the temperature distribution within the solid, and then you can calculate the heat transfer from the solid to the fluid. Subject to the condition that the value of H is known. The question is, how do we get the value of H?
Yes, sir.
That is what is being attempted to be addressed over here, how to find out the value of H. And when we talk of finding out the values of H, then we are not concerned about the solid as a domain of interest. Now that we are interested in the fluid as a domain, where the fluid as a domain with the solid as a boundary. So what type of boundary condition on the solid will be there? That can be isothermally heated solid wall. It may be isoflux condition. It may be it may not be either a isothermally heated, may not be neither a isoflux type of wall condition. Again, we have to start with a very simple thing, and you can go for complex and more complex things. Now, to begin with, we are discussing about a problem that you have a heated solid wall with some temperature, known temperature maybe. The whole wall is known, having a known temperature, and there is a fluid that is moving over this plate, and otherwise the temperature of the fluid is T infinity, and otherwise the velocity of the fluid is U infinity. These are called the free stream values. The velocity at the free stream, the temperature of the free stream, and the pressure of the free stream. And although these are free stream velocities which are constant, but near to the wall there is in fact a velocity variation that varies from 0 to u infinity within a thickness delta. Again, what is the value of delta that we don't know. And similar to this velocity variation, there will be in fact a temperature variation. The temperature will vary within the fluid zone from T0, that is known. If it is known, then you know the temperature of the fluid will be T0, and at the edge of the thermal boundary layer, the temperature will be T infinity. In between, how it varies, that we do not know, and also over which thickness it will vary, that is over what is the value of delta T over which it will vary from T0 to T infinity, that is also not known for us. All these are questions which needs to be addressed in the subject of convective heat transfer. As a standalone, you may have studied this thing, how to find out the value of delta within which the velocity is changing from 0 to E infinity. That may be taught in the subject of fluid mechanics separately. But when we talk of the convection heat transfer, you may find out delta T separately if it is a forced convection, and if it is a natural convection, then there will be a strong interdependence of the heat condition that will cause the velocity. So velocity independently cannot be found out until unless we find out the temperature distribution. They are interlinked. For the case of natural convection, the variation of U will be very much connected to the variation of temperature, because it is temperature that is causing the fluid to flow. So independent of the temperature variation, we will not be able to calculate the velocity variation for the case of natural convection. But for the case of forced convection, this movement is not because of temperature driven flow. The movement is because of some externally imposed velocity field. So for the case of forced convection, we need not to know how the temperature is changing if we want to find out only the velocity variation. So velocity variation is not dependent on temperature for forced convection. But for natural convection, the velocity variation is in fact the movement of the fluid is because of temperature. So it is a thermally driven flow. So if you want to find out any answer for the velocity variation, you have to know how the temperature varies, and also the temperature variation will be controlled by the velocity variation. So velocity variation will depend on temperature variation. Temperature variation will depend on velocity variation. They are interlinked. They are called closely coupled with each other. You cannot find out solution for one independent of the solution for other. It is like a solution of simultaneous equation involving two unknowns. One unknown is u, another unknown is t. So if you want to solve for u, you have to know the solution for t, and if you want to find out the solution for t, you also have to know the solution for u. You have to solve them simultaneously for the case of natural convection. That is somewhat more complex. We'll come to that later on. But to begin with, what is the question that we require to answer? That is what I am trying to introduce. In convection heat transfer, what is the question that we want to solve? Many times we do not know the question after the entire amount of study. What was the basic question? What was the basic question in case of conduction heat transfer? To know the rate of heat transfer within a solid under subject to different boundary condition. May be subject to known temperatures on the wall, may be subject to convection condition on the wall, on the surface of the wall, and that convection coefficient is known. But in case of this fluid convection heat transfer problem, we are interested to find out what is the value of H. Now question is, how do we find out the value of H? That is what we'd like to find out. Not only the value of H, we also like to know when the fluid moves, it tries to move down this plate, or if you keep this plate intact, then it is exerting a drag force on the movement of the fluid. The fluid is being tried to be dragged back. That is why there is a slowing down of the velocity. So what is the force the wall is exerting on the fluid, and that force is equal to the force exerted by the fluid on the wall. They are equal in magnitude and opposite to each other. The fluid is trying to push down the wall in the downstream direction, and the wall is trying to slow down the movement of the fluid by exerting a drag force in the backward direction. And the magnitude of these two are same, but their magnitude, their signs are opposite to each other. So that is what we are interested to find out. Why you are interested to find out the force is because if you want to keep the plate intact, it has to be grouted. And what is the to design the grouting of that wall? You require to know how much is the force that is falling on this wall, because if the grouting mechanism of this wall is not strong enough, then it will be washed away by the fluid. So if you want to design the grouting of the wall, the support of the wall, the foundation of the wall, you must know how much force is being exerted on the wall with the by the fluid. So we require to know what is the force exerted by the fluid on the wall or by the wall on the fluid that we want to find out. So the question that we want to know in the case of convection heat transfer are these two questions. One question is the force exerted by the fluid stream on the plate. And how do we find out the force? That we can find out if you know what is the shear stress exerted by the fluid multiplied by the area of this flat plate. Now the shear stress may not be uniformly acting throughout the length of the wall. Shear stress may vary around the length of the wall. So if we know what is the local shear stress, and then we can integrate that local shear stress over the area of the plate. And what is the area of the plate? That is the differential area is given by dx, a differential length into the width of this plate. The width of this plate or the depth of this plate is along z direction, where this is the x direction is the the streamwise direction, y represents the direction across the stream or transverse direction, and z is the direction along the width of this plate. The plate has a width that we have not shown. We have shown only the frontal view of the plate. Now, if the width of the plate is W, and if we take a small elemental length dx, then the elemental area on which this shear stress is acting, tau, that is tau into dx, tau is the shear stress, and dx into W is the differential area on which this tau is acting. And if we want to find out the total force, then we require to integrate this over the length of the flat plate starting from x equal to 0 to L, where L is the length of the flat plate. So we can make this integration provided we know how this tau varies with x. W being constant, you can bring it out of this integration. So we require to know how this tau, the shear stress, changes with x. And as we know from your fluid mechanics study, the shear stress is given by mu into del u del y, and that del u del y is to be evaluated at y is equal to 0 on the wall. So this is the wall shear stress that you can find out. Once if you can find out, you can integrate this thing. Now the question is, how do you know the value of del u del y? Once if you know the value of del u del y, then we can find out the velocity gradient on the wall. And once we know the velocity gradient on the wall, multiply that with the dynamic viscosity of the fluid to get the wall shear stress. And once you get the wall shear stress, you can integrate this with respect to x. Now, as you can see, u may be a function of, u is in fact a function of y, that you can see it is varying along y, and also this functional dependence with y is not the same for all x. It is because this, what we'll see is that this u is not only a function of y but also a function of x. So u is in general a function of x and y, and if we differentiate this with respect to y, the dependence on x remains. So this will be a function of x, And if we know this function of x, we can integrate this over x to find out the total force exerted by the fluid on the wall. And that magnitude will be also the force exerted by the wall on the fluid. In only the magnitude will be same, but only thing the direction will be opposite. Now, similar to that, you also have to address a question for the case of heat transfer. Shall I take a 4 minutes break? I take some break.
Surely, sir. Surely, sir.
Take a break and then I'll come back. Let the recording remain open like that.
Yes, sir. Yes, sir. No problem.
Now, in the case of heat transfer, similarly, we can find the heat transfer from the plate as equal to the wall heat flux Q, and if we can integrate this over the area of the plate, the area of the plate is given by the differential area is given by dx into w, similar to this dx into w, and this wall heat flux will vary along x. That's why, because it varies along x, so if we want to find out the total heat transfer rate from the plate, we require to integrate this wall heat flux over the area of the plate, and that we can do by integrating this thing over the length of the plate starting from x equal to 0 to L. Now, how to find out the wall heat flux? This wall heat flux we can obtain by applying the Fourier's law of heat conduction. Although where we are studying this thing is in the fluid domain, and the mechanism of heat transfer is by convection. But fortunately, if the wall is a rough one, and if the fluid has a viscosity, then because of these things, the fluid on the wall will be not moving, which is not a moving one. There will be one layer of fluid that will be sticking to the wall. So that fluid is not moving. So only way the heat is transferred from the wall to the depth of this zone is across the sticking wall of the fluid. There is one layer of the fluid that is sticking on the wall, and the heat transfer passes from the wall to the moving fluid via that sticking fluid layer. So the mechanism of heat transfer in the sticking fluid layer will be by conduction. So we can apply the law of conduction heat transfer, because the layer that we are considering at y is equal to 0 plus, there is a layer of fluid which is not moving. So the mechanism of heat transfer will be by conduction only through that fluid layer, and that is why we can apply the Fourier's law of heat conduction Q as equal to minus K into del T del Y at y is equal to 0 plus. If we take at y is equal to 0 minus, then we will get the heat transfer considering the temperature gradient inside the solid. If we know the temperature gradient inside the solid, we could have applied minus Ks into del T del Y at y is equal to 0 minus. In that case, we could have taken the viscosity, the conductivity of the solid part, and we can apply that thing provided we know what is the temperature gradient inside the solid part. Now suppose there is a case where we don't have access to the solid part. We don't have access to the solid part, we have only access to the fluid, and we have access to the solid only so far as this surface of the solid is concerned. We know what is the condition on the external wall where it is in contact with the fluid, but we don't have any access to know what is the boundary condition on the other part of the solid Also, we do not know what is the value of H. So we cannot solve for the temperature distribution within the solid, so we cannot find out the temperature gradient within the solid. Now here what we have access to is a knowledge about the exterior surface temperature, that is suppose equal to T naught, and we also have the fluid flow knowledge. Now if we can by some means find out the temperature gradient inside this fluid, then we can find out the wall heat flux in terms of minus K into del T del Y. The one subtle difference is that here the conductivity that we require to consider is the conductivity of the fluid, because we have access to the fluid domain only, and if we have a knowledge about the temperature distribution within the fluid domain, just simply multiply this with minus K into del T del Y in the fluid domain and evaluate this del T del Y at Y is equal to 0. So you get the wall heat flux, and once you know how the wall heat flux changes with x, you integrate this over x to find out the total wall heat flux or total heat transfer rate over the wall, and you get the answer to our question. Now that is not our question, it is an intermediate question so far as the convection heat transfer discussion of H is concerned. Now coming back to this thing, what we have done is that we have integrated the wall heat flux over the wall area to get the heat transfer rate. Now if we take the wall heat flux, what is the thing? That wall heat flux also we can write it as equal to the convection heat transfer into wall temperature minus free steam temperature. That is what we are accustomed to find out the wall heat flux. How do we find out the wall heat flux? Is if we know the value of H into delta T. Delta T between the surface temperature of the wall minus the free steam temperature of the wall. And when we do not know, then how to find out this thing? If we know this thing, we can easily find out the wall heat flux, and then you can integrate this over the entire wall to get the heat transfer rate. But when you don't know, then how do we proceed? You also can write this heat flux as minus Kf into del T del Y at Y is equal to 0 plus. If we know this thing, then from there we can find out the value of H. Or in other words, we can write H is equal to minus K into del T del Y at Y is equal to 0 plus divided by T0 minus T infinity, where the T0 is nothing but T at Y is equal to 0. So we can find out the value of H if we know how the temperature gradient is changing along the depth of the fluid and at different values of x. Then we can find out the H at different values of x. Now if we know this del T del Y inside the depth of the fluid, multiply that with minus K into Kf. What is Kf? Is the conductivity of the fluid divided by this T0 minus T infinity, the temperature difference that is causing this heat transfer by convection. Now this we can write it as in a dimensionless form. If we write it in a dimensionless theta as equal to T0 minus T divided by T0 minus T infinity. Suppose we define a dimensionless temperature theta as equal to T0 minus T divided by T0 minus T infinity, and we define a dimensionless y bar is equal to y by L. Then we can write this as H, and if you see this minus del T del Y divided by del T0 minus T infinity, can we write it as del theta del Y? Can we write it as is minus K into del T del Y divided by this thing? Can we write it as this del T del Y divided by this thing? Can we write it as minus del theta del Y with a minus? If we define this theta like this, then what is the value of del T del Y? That will be equal to minus del T del Y divided by this thing. So minus del T del Y will be equal to del theta del Y. divided by this thing. And then you can convert this y also in terms of y bar like this. What is this y bar? Del y bar, from here you can write, before this we can write one thing, that del theta del y can write it as equal to minus del t del y. It's simply nothing but whole into, somehow you can write it like this t0 minus t infinity. Write like this. না, এটা এখানে হবে না, it will be here. Can we write it like this? And also, can you not write it like this? From here, can you not write it like this? Del y, what is that?
So dou y bar by dou y,
हाँ,
তাহলে 1 by L আসবে, হ্যাঁ।
বারটা আবার কোথায় আছে? বার, is that bar? এখান থেকে কপি করে নি। This will be equal to 1 by L.
Yes, sir.
তাহলে can you not write it like this? This H will be equal to K into del theta del y bar into 1 by L. So this will be equal to this thing. So H into L by K, H into L by K will be nothing but equal to del theta del y bar at y bar equal to 0 plus.
Yes, sir.
H into L by K. Now this is a group of parameters that is equal to del theta del y. Now what is the dimension of this thing? Theta is a dimensionless temperature, y bar is a dimensionless distance, is dimensionless. And if you see H into L by K, that is dimensionless. H is watt per meter square Kelvin, and this is meter, so it is watt per meter Kelvin, this is also watt per meter Kelvin, so this is a dimensionless thing. It's called this is a number that we call it as Nusselt number. Nusselt number is given a symbol Nu, and this has a length scale L. Based on that, there is suffix you indicate. You can write Nu or Nu suffix L given as H into L by K. Now you see this is very similar to another number that we have just come across called the Biot number. What is the difference is that in Biot number you have a similar type of expression HL by K, but there that K stands for the conductivity of the solid. And when you talk of Nusselt number is the HL by K again, but this is a conductivity of the fluid medium. So this is a dimensionless number that people try to find out Nusselt number as a function of the flow condition. In a forced convection, this will see that this will depend on the Reynolds number, Nusselt number. So what people try to do, the researchers who work in this area, they try to find out what is the dependence of this Nusselt number on Reynolds number and other fluid property like Prandtl number. So they always try to find out a correlation between Nusselt number as a function of Reynolds number and also as a function of the fluid property. Uh, so once you know the velocity condition, from there you find out the Reynolds number. From there you can calculate the Nusselt number. Once you know the Nusselt number, from there you can find out the value of H. H will be now Nu into Kf by L. So what people try to do is to express different type of equation such that through that equation you can find out the value of Nu. Once you know the value of Nu, the Nusselt number, from there you can find out the value of H, and we are interested about the value of H for a particular Reynolds number. So you can find out H is equal to Nu into K by L. But how do you get the value of Nu? That is the subject matter of convective heat transfer. So from convective heat transfer study, you can find out how Nu depends on RE, and once you know RE, you can find out Nu. From Nu, you can calculate the value of H. Okay. So all these questions, if you want to find out, then you have to find out how theta varies with Y. Once you know how theta varies with Y, you can calculate Nusselt number, or you can calculate the value of H. H you can calculate if you know how theta varies with Y or Y bar. Question is, how do you know how theta will vary with Y? Again, that is what we have to find out in convective heat transfer, the theoretical convective heat transfer, where from you can find out how theta will vary with Y. Once you know this thing, you can get the value of H, or you can get the value of the corresponding dimensionless term. H and Nu, they are the same thing expressed in two different mode. H, when you give it in this form, is a dimensional form. You can give H in a dimensional form, or you can give Nu in a dimensionless form. One is the replica of the other expressed in two different forms. This is expression of H in a dimensionless form, and this is expression of H in a dimensional form. Knowing this thing, you can find out this. You don't require to find out this thing, but if you know Nu, you can find out H as simply Nu into Kf by L. So question is, how do we find out this thing? To find out the value of H. That is the subject matter of interest for convection heat transfer. This will continue in our next class. Okay, let me stop over here.